So today we are doing problem 1584, mean cost to connect all points. Essentially we just got points and we rate distance by, so cost of connecting is their Manhattan distance, which is absolute difference of coordinates, and we wanna basically minimum cost to connect them. This screams that you want MST, and usually this works in a way that you have a graph and either you use Kruskal, so you sort edges by weight and use union find to keep check if adding the vertex creates cycle, if not you add vertex, if yes you don't add it, or you use prim's algorithm, right? So this would take, here we don't have edges, so edges are, there is n squared edges because from each vertex to n minus 1 vertices, so n times n minus 1 divided by 2, but whatever, so O(n) squared edges. And we would have to sort them and then iterate over them and do some linear, like constant time thing, because Ackermann function, so n squared log n. On the other hand, prim algorithm starts by saying that okay, our MST just consists of this vertex and then we add vertices, right? So we check distances to each vertex, right, and pick the closest, right, and then we update distances, right? So for each vertex we added a new one, so now we have to check if edges from that vertex to the non-MST vertices are smaller than, like if this is smaller than this, and this than this, and this than this, which is in all cases. And now time complexity of this is we also can do this in m log n, or no, this is n log, no, I mean if we store the vertices in a heap, not sure really about prim, but I mean I guess if you have like so what will n minus 1 edges, and for each iteration, so it take like what, log m, because we know log m, or will it? I mean we will have to update the edges, so edges what's the time complexity of a network? Because okay, let's say I have yeah, so so when we update we push all like O(n) edges there, and in total therefore we push n squared, so there's not just n iterations but n squared iterations, and for each of them we do log n squared, which is just 2 log n. So O(n), so same time complexity. Now what we can realize is that actually, you know, prim takes m times log m, right? But, and this is a but, we can do it in n squared, which is usually bad, but let's take a look at coordinates. Oh wow, 1000, great, 1000 points, so n squared will be best. And so this will work in a way that for each vertex, first of all, we mark if it's inside of MST or not to check if we are not forming a cycle. Second, for each vertex, we store its minimum distance to MST, right? And each time we pick minimum, right, this way we only add the n-1 edges directly, and for each of them we first in on check minimum and then in on update the distances, and then we get n squared. So n is, so let's do that. So first let's grab the length of the points, right, and then in MST is false times n, and then this will be like min dist float inf times n, min dist 0. So let's say 0 is in MST, right? 4 in range n-1, right? And then we pick min node, no wait, so that's min distance float inf min node for node in range if so n iterations actually, or n-1, right? And if min dist node min d min dist node min node, right? So we got the node to which there is smallest distance, so we take that. So actually we want to do n iterations because, right, and then MST cost is this, right, and then MST cost plus equals and not in MST node. Maybe we can do that first because that's faster to check, right? MST cost min distance, and then in MST min node is true, and then for node in range n, if not in MST node, then we want to do weight is apps points points min node 0 minus points min node 1, and then we want to do if min dist node min dist node weight, and then return MST cost, and that immediately works, and that's almost fastest. Fair enough. So let's quickly write up solution. So prims MST O of n squared. Okay, so we have normally Kruskal's, so this is just an MST problem. Kruskal's algorithm takes O of n log n and prims takes O of m log m. Okay, in our case, okay, so where number of edges and m is the number of nodes, in our case m is equal to n squared, which means both algorithms are, and the usual prims algorithm takes, which means both algorithms take n squared log n squared O n squared log n. Which means both algorithms take. Okay, but if we do not use min heap prims, the prims algorithm with min heap, but there is also a n squared implementation of prims algorithm, which does not use min heap. It just finds the closest node by trying all nodes and then updates all nodes. Now, reality, this version of the, but in proper MST problems, this version of the is not usually used. Since we add vertices to the MS by checking which one is the closest. since we add vertices to the MST by checking which one is the closest. By checking which one is the closest each time which minimum distances from the MST found so far to each vertex, which also takes when there we do n iterations of on work, giving us our final time complexity of on, since we just have to store minimum distances from current from MST found so far and whether each vertex is in the MST already or not yet. Okay, post cannot post goodbye.